All right, hi everybody. This is Erica Coseco, President of Canadian Society of Hydrological Sciences. Thank you so much, anyhow, thank you so much for joining us today. We have a full webinar. So just to remind everybody that this session is being recorded. So we have reached our max of 100 attendees. We did have other people who registered. If anyone's down the hall from you and not able to jump on, maybe have them join you at the computer. So I will be passing over the, actually the presentation has been passed over already to Rob Chlumsky, who is our presenter today. And once again, thanks everyone for attending. And this is sort of intended as a bit of an intro and a lead up to some of our sessions that will be taking place at the CWRA National Conference in Collingwood in 2 weeks' time. So without further ado, I'll pass it over to Rob. Thanks.
Okay. Thank you. Yeah, so welcome everyone to the webinar, CSHS Hydrology Intro to Our Webinar. My name is Robert Chlumsky. I'm currently employed with Ecosystem Recovery, and I've done some dabbling with R in the last few years. So here just to give you a bit of an introduction. The outline on the webinar itself, I'll give a short presentation here just in PowerPoint just to discuss R itself and advantages in different applications. After that, I'll give you an overview of R and RStudio. RStudio is just basically a GUI for R, which is quite helpful. And then we'll go through the meat of the webinar, which will be an introduction, interactive introduction to R basics. And there'll be some opportunities to ask questions. In fact, I encourage you to. I think we'll probably speed through this in far less than 2 hours if there's no questions. So definitely I encourage everyone to have RStudio open if they can, work through the code, type things as we go. And if anything comes up or you have questions, feel free to type into the chat menu on the webinar, and we'll do our best to get through all the questions. Just for fun, if you're like me and you like to know who's listening in on the webinar, not that this is a complete statistical survey, but seems like there's a relatively good split between sort of the young professionals, the private sector, and the public sector. So that's nice to see. And in terms of the level of experience with R, again, we're pretty split between the 1 and 2. Never have used R before, very little, and the 3 and 4 with some experience. So that's good. Hopefully this will hit the mark here. What this webinar will do, it will introduce you to what is R, why is R, and who is R. We'll get you comfortable writing commands and looking for help in R and RStudio. It will provide you with some resources and links for future learning and lookup resources. It will give you some useful code snippets and ideas of what R is capable of. Hopefully everybody can walk away with some one package or a code snippet or some idea of how they can use R in their own practice. And of course, this will be focusing on water resources and hydrology applications. And given that it's called R, there might be a few pirate jokes. What this webinar will not do, it will definitely not make you an R expert immediately. It's relatively, I guess, quick to pick up. There's a bit of a learning curve, but it will definitely take some practice and frustration before you become an expert with R. It will not provide you with the perfect code for every situation. It will not provide you the comprehensive list of resources, although hopefully some good ones. And it will definitely not provide a comprehensive overview of every water resources related package in R which exists. I find that every time I Google something, there's something new.
Rob, sorry to interrupt, but I think the slides aren't you're not going to the next slide. I think perhaps we're seeing the wrong screen.
Oh, is it stuck on the same first one?
Yeah, it is. Sorry.
Okay.
There we go. Thanks.
Okay. There you go. You can see what this webinar will not do slide?
Yes, we can.
Okay. All right. Sorry. I'll show this just in case you couldn't see the slide. So the breakup is a good split between young professionals, private sector, and public sector, and a good split between level 1 to 4 sort of experience with R. So that's good. All right, carrying on. The webinar materials, I just want to make a quick note that Dr. Kevin Shook at University of Saskatchewan prepared a lot of these materials in a different version, and these have been kind of adapted. So he has a lot of resources for our training resources on his GitHub page and lots of other great materials there. So I definitely encourage you to take a look there if you're looking for other resources. In terms of the materials for this webinar, there should be a few things in the handouts. I see that there's the PDF of the presentation itself, and there's also a PDF with the code. Erica, do you see? I don't think there's the rmarkdown.rmd file, is there?
I think it was handed out. I think it was sent out earlier this week. If it wasn't sent out again today.
Okay. Okay. No, either way, so there's the PDF, which was generated from the rmarkdown file, and the rmarkdown file you can actually open with R, has that RMD extension, and you can actually use that to go along with me as I go through the actual code part of this webinar. So if you have that in an email or some other resource, then you can have that open and follow along as well. And there's also an installer package, .r, just has all the libraries. If you don't know how to run it or have issues with it, don't worry about it. But if you have run that or have a chance now, you can install the packages just to save you some time. Okay, so let's get into the actual discussion. What is R? It's a command line program, it's a GUI-based program, it's a programming language, it's a general scientific program, and it's not just about statistics. Added a slide about the history of R just because it's important, probably not the main focus of what people came to the webinar to hear, but I think it's important. So it was developed in New Zealand at the University of Auckland. Development first began in 1992, and the first stable version came out in the year 2000. And the point there is just that this is not a very old historic language. It's relatively new in its development. And just on a note about syntax, it was developed out of the S language, which was also developed in Bell Labs, and that's also the same group that came up with the Unix system. So if you're a Unix user or familiar with some of the commands there, you might find some similarity with R. So why would anyone want to use R? It's a powerful software. It's excellent for a lot of things, including statistics, which was kind of the first purpose of it, but it also data processing, graphing, analysis, including GIS and solving mathematical equations and things like that. And it's also part of an acronym known as free and open source software, which means that it's free to use, download, you can view the code, change it, all that kind of stuff. And with that, you can actually see and trust the code and know exactly what it's doing. It's not a black box model where you only see the output. It works with standard file formats. There's no proprietary issues there with licensing. And as we'll see, there's a large amount of development happening currently with it. There's a very large and expanding user base, and therefore there's a lot of things that have already been done. You don't have to reinvent the wheel every time you need to look at a new function. As well, it works well with other programs, interfaces with languages like C and Python. You can read and write directly from Excel packages, plays pretty well with all sorts of programs. You can even read in shapefiles, databases, NetCDF, and other kind of funny formats. And something that's nice is that it's also more or less platform independent. It works basically the same across Windows, Macintosh, and Linux distributions. If you're like me and you work in Linux laptop at home and Windows computer at work, you can actually have the same code run pretty much without issues across both of those systems. And just as a note, maybe this is improved, but I know Macintosh, if you try to open Excel files or other files, you have all sorts of funny conversion errors between them. So that's something that you generally don't get with R. This is a funny quote. I was talking to someone who said that R is a program used by ecologists because that was the bubble that she was familiar with. So I found that kind of funny. R is quite popular in ecology, but of course it's used by far more than just ecologists. Statisticians, as I mentioned, that was kind of the first purpose as a statistical analysis program, but certainly engineers, biologists, researchers, all sorts of practitioners, and people in many other spheres outside of water resources engineering. So it's quite a popular program. This is a fun slide from, again, Kevin Shook. Spreadsheets must die. What are some of the qualities of spreadsheets? Generally speaking, they're slow, dangerous, unreliable in that it's hard to know that your data hasn't been changed or formulas haven't been adjusted once they've been opened and saved by other people or copied and pasted and that kind of stuff. and it's not great for embedding documentation in terms of what was done to change formulas, where the data was from, what values were pasted over, which ones are formulas, and all that kind of stuff. As an additional note, Excel included is a proprietary program, which means that at some point, if support for that program drops off, or it's an old version, or you don't have the license for it, it can be hard to access that data. Excel is maybe slightly better than some other programs, but generally speaking, proprietary programs mean that you can 100% rely on being able to access that file in the future if you don't have the right license or software changes. That being said, this is a caveat to Kevin's original slide, but spreadsheets are certainly hard to avoid in many professional settings, but it is important to understand their limitations and how easily errors can be hidden, or you can miss things that were, pasted values over formulas and things like that. So just a note of caution when using spreadsheets. So as I mentioned, what is R used for? Lots of things, including statistical analysis, data processing, including sort of big data processing, publication of very nice high quality graphics, including for papers and journals and reports and things like that. You can do a lot with GIS directly in R, data visualization, all sorts of things, machine learning models, etc. So it's definitely developed far from just the baseline statistics program that it maybe once was. So of course, it still has basically every statistical test under the sun that you can think of, so you don't have to rewrite any of these from scratch. They're likely is already embedded in R, or there's a package in R that supports many of these tests. In terms of plotting and scientific graphing, it is certainly one of the best programs. Here's a few examples from Kevin Shook's slides about just different plots that you can make with R. As I mentioned, R is capable of performing GIS analysis directly, so you can do importing shapefiles, rasters, clipping operations, all those sorts of things, and make as well high quality outputs with it. And just to show that this using GIS in R is not quite as difficult as one might think, this is just a very basic plot with a raster and putting a shapefile of a creek over top of it, and it basically comes out to just importing the data and plotting in 2 commands. So it's not a 23 lines of code to get one plot to work necessarily. This is a cool slide just with visualizations. So there's a lot of people that spend a lot of time developing packages in R that are all freely available. This is a neat one that I found that basically does 3D visualizations, including from different perspectives, shading visualizations based on the sun angle and things like that. And on the right, you can also see that's basically water depth made in a transparent layer, and you can in R play with that, rotate it, see it from all different angles. So yeah, anyway, lots of excellent visualizations that you can see and perform with R. R also supports machine learning algorithms, which is a pretty hot topic, especially in water resources and other fields today. And there's lots of packages that support those types of analyses. Web applications, there's something called Shiny in R, and you can actually develop HTML embedded interactive data tools directly in R, and there's different ways to host them online and basically embedded in websites. So there's a lot that you can do in web development with R as well. And there's a link if you're interested later to go and look at different examples of Shiny projects. The typical workflow with R is reading in data files, whether it's text files, databases, CSV, shapefiles, etc. You do some sort of quality control and exploring the data, making sure that everything is fitting in terms of filling in missing errors and that kind of stuff. Exploring and visualizing the data set to get a feel for the data, perform whatever calculations you need. You can save the results, export data to other programs, and from there create high quality graphics. And all of this is basically embedded in some sort of script, presumably, and then everything can be documented and repeated and automated for lots of different tasks. So as I said, everything can be done as a manual sort of one-off script. If it's something quick that you need to do, or if it's a task that you plan to perform many, many times, you can quickly throw that into a loop or a package and have that automated for future use. It's relatively easy, especially compared to something like Excel, to have all sorts of logging of what it was done and leave the raw data as is, imported into R and output exported data for future archiving. All data results are stored in standard non-proprietary files. typically you can output into text files, CSVs, or anything like that. So there's no real issues in terms of data siloing or format issues with your projects. So if you have, as long as you have your raw data in some format that can be read in, R is free and open source and outputs into things that can be read with Notepad if needed. So you won't have to worry about losing your data due to proprietary issues. So some of the challenges with R, of course, if it was super easy, everybody would be using it immediately. There is a bit of a learning curve with R. I've found and talked to different people that, especially if you've worked in other programming languages, such as MATLAB or C, R can be a little bit difficult to pick up. It is kind of non-intuitive compared to some other languages. And certainly if you've never done programming, it's a hurdle there. But that being said, there is lots of help available. As I mentioned, there's a huge number and a growing number of users. So there's lots of resources on Stack Overflow and other forums if for any problem that you have. The RStudio interface makes it very easy to use, or at least a lot easier, does a lot of stuff for you. And there's lots of resources like the reference card here that you can find in a PDF file, and it has most of the most useful commands at your fingertips. So there are lots of resources and people to learn from if you are picking up R. In terms of the number of packages, as I mentioned, there's a huge number of packages. There's something called the CRAN repository, and that's basically a central repository for R that's embedded right into RStudio. You can easily download packages there. And there are a huge number of packages growing on there. So as I mentioned, you probably won't need to reinvent the wheel. There's a fair chance that if you're trying to do some sort of relatively standard process, there's probably already some package available for it. And the nice part about CRAN is that everything is sort of checked and vetted and debugged for errors before it's posted, and so you can rely on the compilability of that package. As well, there's also sample data, documentation, and help files that come with all those packages, and so there's plenty of help available to use new packages. And one thing, if you're a Python user or former Python user, I found that installing interdependent packages can be a bit of a pain, and that kind of stuff is handled directly in R. I know at some point R and Python are fusing together, so hopefully those types of things will be resolved, but at least in my experience, dependency with packages is handled very nicely in R. And this is just the plot to show the number of packages ever published on CRAN. I apologize, you probably can't see the access labels very well there, but this is from 1997 to 2019, and you can see the number of packages is growing exponentially. So just to emphasize the point that you probably don't need to reinvent the wheel as long as you have some basic R under your belt. So of course, the reason why probably most people are here on the webinar are in hydrology. There's a large number of research groups and institutes and consultants and practitioners using R in the field of water resources. And there's many packages that exist specifically for these types of applications in water resources. Of course, the one we're kind of talking about today and will be at the national conference in a couple of weeks or 10 days, as I've been reminded, the CSHS hydrology package for Canadian hydrologists. And there's plenty of others, including eco hydrology, which has a lot of things related to eco hydrology, like baseflow partitioning. There's a package for hydrologic time series management, one for goodness of fit statistics specifically. There's a tidy HyDat package, which we'll look at in a bit once we get into R, which can be used to scrape Water Survey Canada station data directly. And as I mentioned, there's hundreds, probably more, that are not listed here. So that's basically the webinar presentation portion. Next, we'll get into the actual RStudio going through some code part. And the agenda for that will basically be a quick introduction to the RStudio interface. We'll get into some basic R syntax, you'll figure out how to find help in R, which is probably the most important thing you might take away from this. We'll get into actually exploring and installing new packages, which is pretty straightforward, but I'll show you how to do that. We'll go through reading in data, creating plots, and all the typical programming stuff like if statements, functions, and loops. So this is basically time to switch gears. I might take 30 seconds here just to see if there's any questions from the first part of the presentation here before we get switched over.
I believe all of the presenters all of the participants have been muted, so I'll just ask people to use the raise your hand tool if you have a question, or type it into the questions box, please.
Yeah, the question box is maybe the easiest. We're keeping a close eye on that here, so that's probably the best way. If you do have a question, just to type it out. So Just in terms of moving on to the next stuff, I know there are maybe a couple issues with R and R Studio installation, so you may just have to follow along, but hopefully, for the most part, everybody's already gone and installed the base R package, which is at the rproject.org, the RStudio interface, which is rstudio.com, and run the installer for different packages, and has the PDF of the webinar, which I believe is available in the handouts here for the conference view. So I'm just going to switch gears here. Eric, you'll have to let me know if you can still see RStudio.
I will.
Erica, sorry, can you see the RStudio screen right now?
No, right now I see what I'm guessing is your PowerPoint screen.
Okay.
Not the presentation though.
I'm going to try something here.
I think I see it now. So you have 4 windows in it?
Yeah.
Okay.
Okay, how does that look?
That's good. I think there is a question in the question box, if you're able to see it.
Sorry, just pulling up the questions here. I've lost it now that I've changed everything around.
I can read, I see 2 of them. I can read them if you wish.
Sure.
So one question is, what is the definition of a workflow in R?
I don't know if there's a real definition for that, but just sort of the typical what you would do for a project or data analysis. So typically what you would need to do is pull in the data, visualize it, get a feel for it, do something with it, some sort of analysis or a statistical test, and then output and save your results. And basically the emphasis there is just to show that what you do with R is a little bit different from something like Excel, where you have your data and do the analysis and do that all in sort of one file. With R, typically you would have some sort of archive for your raw data, and then you pull it in and create a different login directory for the analysis, and your script and all that analysis is in a separate area, if that makes sense. So hopefully that answers the question.
That's great. And I'll just ask, there's a second one, and I'll just make this the final one before we move on. Can R be used to develop, design applications, i.e. standalone apps?
Standalone apps, so there are, I suppose it depends what you mean by apps. So there's, for example, the web applications like that you would make with R Shiny. Those, I guess, are standalone in a sense that you can embed them in web pages and use them for whatever purpose you need. In terms of just a standalone app that you would open as a, let's say, an exe file or some sort of executable, I don't know if it can be done to do that. R can do a lot, so I wouldn't be surprised if you could convert it into an exe. Like I know you can do that with, let's say, Python and MATLAB. To my knowledge, I haven't done that, but it is quite good at making, as I mentioned, packages that are useful in an R context. So yeah, I'll have to get back to you on that one, whether it actually makes executable files or not.
All right, I think that's it for the questions. So we can move on if you're good.
Yeah, that sounds good. You can probably see my chat window here, but I don't see anything coming up, so I may just have to rely on you, Erica, to facilitate some of the questions.
Not a problem.
Okay, sounds good. All right, so this is just getting into the actual RStudio portion here. When you open up RStudio, you'll probably find that it has a white background. If you go to Tools, Global Options, and Appearance, you can pick whichever one you like here. I like the dark background, so hopefully that's okay with everybody here. Just as a quick introduction to RStudio, so just emphasize this is just the user interface. The actual R program looks quite different, but as I mentioned, RStudio is quite a nice interface for just making your workflow a little bit easier and controlling what you see. You can look at your files directly, things like that. So just to start from the beginning and give you kind of the full overview here. If I close this stuff, this is probably more what it looks like. So this is called the console. This is basically where you can type in, commands interactively with R. So for example, if I say 1+1, that's a command, it gives you an output. I see it directly in the console here. Over here, you should see an environment window, and this is basically where all of your variables, functions, loaded data, that kind of stuff will be stored. Right now it's empty because I don't have anything stored in terms of data or functions, at least nothing that's outside of the package, so to speak. But anything that would happen that stores data would be found in the environment. And then down here, this is another window where it has your files, plots, packages, etc. The files window, right now I'm under my downloads folder, and these are the files that are here, so I can see the Active Directory and which files I'm looking at. So if I open up this markdown, there I have it. If we go to plots, any plots that you output, which we will do at some point, will be outputted here. Packages is just a list of all the packages that are basically downloaded and installed with your R on your computer. So you can find them here and see which versions they are and things like that. The help window is probably the most important. We'll get to that, but anything that you do in terms of looking for help or searching for functions, things like that, will show up in the help window. Okay. I guess a couple helpful shortcuts. If you go, at least in Windows, between Control-1 and Control-2, you'll bounce back between the console and this area. This is basically where any files, R files that you have opened will be stored. If you go File, New, or just click on this plus window here, you'll see you can basically make a new file. So for example, if you open up a new R script, this is now basically a text file with a .r extension. You can save it, work with it, do what you need to do. So for example, if we go 1+1, 1+3, very simple stuff. This is just storing in a text file. And then if you want to run it, it will basically output to the console. So I'm just going Control Enter or hit run. And that will basically just output it to the console, and you can see that result is in the console window. And then if I wanted to, I could save this. If I'm working on it, do something else with it. So that's basically a layout of what the RStudio interface looks like. Are there any questions on the interface itself?
I don't see any in the window here.
Okay, we'll keep going. So as I mentioned, this is a markdown document. So this is what it looks like in R itself. So this has all the commands and stuff embedded. I believe everyone should have the PDF version of this as well. I think hopefully it's visible on my screen right now, but basically this is what the PDF looks like. You can see this is formatted pretty nicely, and the way it works is you go from the R code, you have these things embedded. It has different rows about syntax and formatting and how it outputs. And I actually have the R code directly in this document here. And when you go to actually knit the document, as it's called, it produces this PDF, it evaluates the code directly, and it puts the output right into the document. So I'm going to be following along in RStudio just so that I can be executing all the different R commands as we go. If you prefer, you can do that if you have the RMD file, and otherwise you can feel free to follow along with the PDF on your own screens, and it should be the same in terms of what's there and what's outputted. And I definitely encourage everybody to go through and follow along and type the commands in and struggle with actually putting stuff into R as we go, so that we can generate some questions and hopefully walk away with more of a working knowledge of what R actually is. So you'll see here that basically, obviously headings are bolded, the text is a normal text, and then what you see here with the orange, with the preceded by a hashtag or a pound symbol or octothorpe, depending on which generation you're from. These are all comments, and with this orange highlighting here, anything that you see with the blue is basically some sort of command. Green is generally in quotations because it's a string. And then after a command like this print command here, you'll find that there's the double hashtag, double octothorpe with what the actual output from that command is. So you'll notice this print line here. If we go back into RStudio, this is where it's embedded. And if I run that command, it's now outputted this statement here. So basically, this is just to show that in this markdown document, it's command and then typically followed by what the output looks like. And this is all embedded nicely in the PDF so you can see exactly what it is. Okay, so we'll move on just with very basic R syntax. And again, please feel free to type in questions as we go. This is meant to be a pretty interactive type of webinar, so ask lots of questions. So let's try some basic math here. As you saw, if I just go 1 + 1, 2 × 2, anything like that, this outputs directly into the console here. You see the result. This output is typically at least one, just as one value. The terminology is an atom, so it's basically just one value. It's not a vector, it's not a matrix, it's just a single value. And you'll notice that my environment window is still empty, and the reason for that is all I've done is run this through R. It outputs to the console, it computes the result and spits it back out. It's not actually stored anywhere for use. Okay. You will find that if you are new to scripting, well, maybe don't worry about this too much if you're new to scripting, but if you've done some programming, this is an object-oriented language. So typically, there's different objects, those have properties, and then we write functions to operate on those different objects. So as I mentioned, the simplest type of object is called an atom. And that's just the sort of single value item. Another note here is that R is not strict on the definition of different data types. So similar to kind of Python or MATLAB, if I assign something and it has let's say a numeric value, and I reassign it with a string value, R will happily reassign it and not raise any flags. In some other languages like C or VBA, if you declare something as a number, as a numeric value, it's always a numeric value. And if you try to reassign it or do something that would force it to become a string, you'll get an error. And so that doesn't happen with R. You can reassign pretty happily. And on the note of assignment, there's a lot of, especially if you follow any R memes, not that I do, but there's a lot of ideas about assignment. You can use an equal sign as you do in many other languages, but the typical syntax with R is to actually use this arrow. And the way the arrow works is it's pointing into the variable that's being stored. So if we go through a few examples here, if I want to now create a variable called A, assign it a value of 1, you can use this arrow operator. If I run that command, you'll see this console, it ran the command. It didn't provide an output because in this case there wasn't any. It wasn't outputted directly because it was stored into a variable, so it doesn't necessarily need to output that value. And you'll see now in my environment window under values, you now see A with a value of 1. Okay. And now as a command, if I just type in A, now I'll see the output. I see it has a value of 1. Similarly, I can do A = 1. It will do the exact same thing, store A with a value of 1. But as I mentioned, in R, typically the arrows are preferred. And the reason is that you can use the arrows either direction, and you can actually see which direction that assignment goes. So if I flip the arrow this way, I now see A has a value of 5. 5 gets stored into the value of the variable called A. And now A, if I type this out, has a value of 5. So it's just kind of more flexible in terms of the equal sign. And I guess the other argument for why you'd want to use arrows not equal signs is that the double equal sign is used in logic arguments, and it just helps to clarify that whole syntax. So now as another example, if I go B into value of A + 1, you'll see that B now has a value of 6 because it had a value of 5, add 1, and now we have a variable called B. So you can see that these get assigned and created very simply. Okay. Pretty straightforward there. We'll move into some functions. So obviously functions are something that takes an input, does some sort of calculation, and outputs another value. Let's just get into it. I'll show you an example here. So I'm declaring a function called squared. So this is the function name, squared. We assign it with an equal sign. I guess we could also use the arrow, and we declare that it's a function. We have round brackets, the input variable, and then in these squiggly brackets is what the actual function does, and that will be outputted directly. So if I run this command, I now have, as I mentioned, there's no direct output because it's stored into something called squared. If we look in the environment window, there's now a new header called functions, and there's something called squared. And as I mentioned, it takes in the input value of x, and what it does is it takes that input value and raises it to the power of 2. So now, because R has, sorry, was there something? No, okay. So now because squared is now stored as a function in R will recognize what that is. If I enter it with the argument of 3, takes it, raises it to the power of 2, gives me 9. Similarly, if I check what my value of A is, A has a value of 5, I can give it a variable, and now it provides a value of 25. Okay, and just an emphasis on the syntax, the squiggly brackets always define what's within this function call in terms of what the actual function does, and you can't confuse those with the round brackets or later with the square brackets. The type of brackets matters quite a bit with the syntax, as it does in most programming languages. Okay, and as you've probably seen or can imagine, you can also have optional arguments. So here I have another function called exponent it. It's also a function declared with the arrow, declared to be a function, and it has 2 parameters, a and b. And you'll notice that unlike the squared function, b is given a value of 2 in the actual function declaration. And then in here, I just take a and raise it to the power of b. Pretty straightforward. And what that means is that b is now given a default value in the function, so I don't necessarily have to provide a value to run that function. So if I go exponent it with a value of 3, let's run this first. So exponent it, it's now stored as a function in R, so it will now recognize if I say exponent it knows what it is, and it tells me what the function is. So now if I go here and run it, if I go exponent it with a value of 3, I get the power of 9, or sorry, the value of 9, because it took my value of 3 for A as the first argument here and raised it to the default value of 2, which I did not have to provide. Even though I don't have to provide it, I certainly can. So if I go exponent it 3, 3, that means A gets a value of 3 and B gets overridden with a value of 3 as well, and I get 27.
Rob, there is a question. Somebody is asking, why is there a square bracket, 1 square bracket in the console screen, or?
In the console, yeah, okay. So I'll get to this in a little bit, but basically round brackets are used for function calls. The squiggly brackets are used for defining functions or enclosing if statements and things like that. And the square brackets are used for accessing vector values or like basically indices of an object. So for example, with an atom, it's maybe not intuitive because it's a single value, but it's basically a single value, which means that the first index of that value is the value 1. Or if I say, let's say 2, the first index of this atom, which has a value of 2, is 2. So basically this is just showing that it's the first element of that. In this case, it's the only one, but you'll see later with vectors. Actually, let's just try this here. So if I go C1, 2, 3, this is just basically creating a vector called A. It has 3 values. And if I go A of 2, I now pull out the second value there. So basically square brackets are just used to access the index of those of that variable to pull out different values when there's multiple values to be pulled out. All right. Yeah, we'll see that a bit more clearly in a minute here. So anyway, that's basically the definition of storing functions. Now we're just going to get into the different types of variables and different classes of what variables are. So there's something called the class command. So if you recall, currently B has a value of 6. So if I go class of B, it'll give me numeric. So that basically means that it's a numeric class variable. Similarly, if I say type of, that's a more specific what type of variable is it, and this gives me the value double. Double, if you're familiar with any sort of data analysis or data handling, double is basically something that can have decimal places as opposed to an integer, as opposed to something else. As I mentioned, there's flexible reassignment. So if I go B, assign it with a value of hello world. Now B is a string called hello, comma, world. And if I go type of B, this, as you recall, used to be numeric or double. and now it's a character. So character is basically a string in R. So it just means that it's text, it's not a numeric value. So similarly, following here, I mean, if I go as .numeric, which is used to convert from whatever format to a numeric value, and I close the value 501 in quotations, 501 would be a string. So if I go type of something enclosed in brackets, it'll give me a character type. That being said, if I convert it and add +1, I now get 502 because as .numeric converted that character into a numeric value, and then I can do some sort of arithmetic with it, which if I were just to go 501 +1, this would give me an error because I'm basically trying to add a numeric value to a string, which doesn't make sense. There's a round and floor functions. So for example, if I take 5.6, run it through the round function, this will give me 6. There's a floor function to take it back down. I'll try this to say as .numeric with B. As I mentioned, this will give me basically an NA because it's not able to convert the hello world into a number, which makes sense. Similarly, if I try to go with A, which I've now reassigned, so let's say if I give a value of 1 here, so now it's numeric again. If I try to say as that character and add something to it, it also won't work. So you can't add 2 strings with the plus sign, basically. Similarly, in some languages, I think Python, you use ampersand to tie strings together. That's not the right syntax in R. The proper way is to use the paste function to combine strings. So this is just to show that basically plus signs are for numeric values to add them together. And if you want to put together string values, you use something like the paste function. I'm sure there's a few different ways to do this, but just make sure that you don't use the plus sign or the ampersand to try to tie together string values, because I think that's something that you can do in Python, and that's not the right syntax in R for people like me who came out of Python. Okay, maybe 10-second break here if there's any questions. Now would be a good time.
We do have a couple of questions. One is there a reason why the squiggly bracket for the end of the exponent function is on line 104 rather than line 103?
Good question. So this is basically just a difference in how you like to define the function. There's actually no functional reason why you couldn't do something like this and just have it all on one line. And it works the exact same way. It's just whether, depending on how you like to lay out your code and what kind of programmer you are, if you like to minimize and have everything on as few lines as possible, or if you like to see the structure of everything and have it on multiple lines. And different guidelines will tell you different things, but functionally it works the same way. It's just how you like to see your code laid out. And for something like this, it probably would make more sense to have it as one line, but obviously as you get to more complicated functions, you want to have it sort of spread out so you can actually see things more clearly. Yeah.
And then there's another one about how someone is able to see the global environment panel. I guess they're only able to see their console. I don't know if you can easily answer this.
Okay. Oh, yeah, good question. So if we go to, if I can remember, view, and then there's different, I guess there's some shortcuts, but basically go to view and then you can tell our studio to show whatever panel you want. So for example, if you've lost the environment panel, just go to view, show environment, and you should have it pop up. And if that doesn't work, right back and we'll try something else.
All right, and then related to the formatting, someone's asking if spacing matters.
Spacing, yeah. Good question. I believe that with functions, I guess not really. With the assignment, it also doesn't matter. So if you go, for example, take out the spaces between A and 1 and do it like that, then it doesn't matter. Obviously, if you're assigning function names, you wouldn't be able to call something, for example, A1 with a space, because variable names need to be one continuous string. So you could do something like A_A, give it a value of 1, and that's fine, but you can't have spaces between variable names. But I think other than that, in terms of functions, calling functions or defining functions, I think it's pretty flexible in terms of spaces.
Okay, and we'll just make this one our last question. Can we move on? How can you clear previous values and functions?
Good question. So there's a few ways to do it. I can never remember how to actually do it with the interface, but if you go to the console and you're on Windows, Control L will clear what the console is. I'll take a second just to say that in the console, you have the whole history, which you also see under the History tab. These are basically just all the commands that you've inputted. So you could actually wipe these out with this broom, and that will actually clear your entire history. But the history is useful because if you go up or down arrow when your cursor is in the console here, you can actually bring your previous commands back and scroll through them, which is kind of helpful if you've entered a command, you take a minute to do something else and then you want to rerun that command or get that syntax you've written out back. You can actually use the up arrows and down arrows to scroll through your previous commands to find them. But if you just want to clear the console just to have a clean slate, Control L will do that, and you can also go into the history and clear it with the broom. And then if you go back to the console, try to up arrow, down arrow, it won't be there anymore. And to actually clear the variables, similarly, you can use this broom here, and this will clear everything from the workspace. And generally speaking, if you restart your R session, that stuff will also disappear unless you save your workspace. But yeah, the broom in the R Studio will clear all that kind of stuff.
Okay, I think we can move on. Just to note that some of the participants have been having trouble with the sound cutting in and out. I haven't experienced that here. We've connected through the phone line, so I don't know if it's something with the voice over internet, but anyhow, sorry to those who are having trouble. Hopefully you can either try to dial in through the number provided to see if that makes a difference, or hope that it improves, I guess. Thanks.
Okay. Erica, you said you've been able to hear me pretty clearly on here, right?
Yes, we haven't had a problem here.
Okay, so hopefully not on my end here, but I'll try to yeah, speak close to the microphone anyway. Okay, let's get back into text here. So we've looked at numeric values and text values and how to combine them or not combine them. There are a lot of text operations to work with string values directly, as there are in most programming languages. So I've alluded to this paste function here. This basically is kind of like concatenate in Excel. It basically pastes together different string values. And you can actually in here use direct string values, and you can also put in variables. So for example, A is 1. A has a value of 1, let's say. I'm using as.character to convert that numeric value to a string. And now I basically have another string called coconuts in my pocket. If I pay 0, I now get one single value that has 1 coconuts in my pocket. And that doesn't make sense grammatically. If I reassign A with a value of 3, I can now change this to 3 coconuts in my pocket, for example. If I use the sprintf function, which you'll probably recognize from other languages as well, you can actually provide proper formatting. So if I run this, I now have $% point to F. This percent is basically an escape character to show that this is not part of the string. This is some sort of formatted item. And point to F, you can basically go through the help and find what the formatting means, but this is basically something, it's a fixed format thing with 2 decimal places, which is why it appears with 2 decimal places here. And similarly, I can basically mash this stuff together, put in my value of A, and put in some value here. So if I run this, I have $3 in my pocket. Now I'm rich. If I want to change this, I can say I have $3 in my pocket. Now I'm still poor. So you can basically work with whatever formatting you want here. And there's different fixed format or general. Here you see %s for strings. So I'm basically inserting a string here. So depending on what you're putting into the sprintf function, you can put in the format characters properly and use that to make one single string here. Okay. So there's, I'm sure, a lot more to say about strings and manipulation, but that's at least the basic stuff there. Okay. So just moving into vectors and matrices here. So as the previous question with the square brackets previewed, obviously R wouldn't be very useful if you could only have one value stored at a time. So there's vectors and matrices. There's also data frames. Basically, a vector is just any set of atoms put together into one sort of long string of values. A matrix is, as you can imagine, sort of a 2D numeric item, and a data frame is similar to a matrix, except that you can mix vectors. You can mix numeric and string values as well. You saw me use this earlier. The C function is basically just the concatenate function, so that's used to create vectors of multiple items. So if I go C 1, 2, 3, I've now created a vector, and this just concatenates the values that I've inputted 1, 2, 3 into a single vector. So if I go here and say A has a value of 1, 2, 3, 4, 5 concatenated, A now has one variable with those 5 values in it as a vector, and you can see that there. One cool thing, I guess that won't work, but let's say B has a value of 2, and if I divide it, B is A over 2. I basically now taken the value of B and divided it by every value in A, which is kind of a neat thing in R. Typically, there aren't a lot of for loops that you see, but if you apply a function to a vector directly, it will basically take that function and apply it to every value of that vector automatically, which is definitely one of those sort of steep learning curves, quirks of R, things to get used to that don't necessarily work the same in other languages. But similarly, A has a value of 1, 2, 3, 4, 5. If I go A over 2, it takes every one of those items, divides it by 2. I think I still have my squared value in here. So similarly, if I go B is the square root of A, it will apply that function to every value in A by default. So there's just a little preview on vector operations. Matrices and data frames will cover in a bit, but they function similarly. So here's the important part with R. Hopefully, if you're going to take away one thing from from this R webinar today, is how to get help in R. So for example, here's the rep function. This basically creates a repetition, and similarly, sequence you can use to create a vector between the values of 1 and 4. The repetition function, as you'll find out in a second, basically takes the value of 1 or whichever value input and repeats it a number of times. And if you didn't know what that was, you could go help rep, and it will give you this help page here. As I mentioned, every package in CRAN has basically a help page like this for the package itself and all of its functions. And so all of these help tips on how to use R, how to find functions, what the functions are, what input values they have. If you scroll through, there's more detailed discussion. There's the values that you input, output, and some additional notes on how to use it. If there's a reference on who created it, or if it's some sort of statistical test, the paper on that will usually get references. There's some other related functions, and there's examples here. So if you didn't know anything about the rep function, here's lots of examples on how to use it. And similarly, if we go help for the seq function, that's SEQ, you see that this is in the base package, so just base R comes with your R installation without installing additional packages. Sequence generation, here's a description, the usage, arguments, examples, etc. So if you just go single question mark, any function name, you'll get a help page that looks like this for that function. If we want to search for a function that we're not totally sure what it's called, but we just want to search by a keyword, we can go double question mark variance, and it will basically provide a bunch of search results that have the word variance in it. So for example, evaluating covariance functions, and you can scroll through here and see if there's one that's applicable to your function. In R, there is something called the var function, which is just short for variance. Typically, when you're writing code, you don't want to have to write variance out every time you want to actually calculate a variance. So a lot of the commands are shortened, kind of like rep and seq. But if we want to see the code directly for a function, you can actually just enter that function without the round brackets. Again, if you wanted to run it, you use round brackets, but if you just want to see the code, you can run that, and you'll actually see the code for that function pop up in your console. And again, that's part of sort of the free and open source part of R, is that none of the code is basically hidden from you. If you have a package, you could dig around and find what that code actually does, save it for yourself, modify it, use it for what you need. One quick note here is that some of the functions, like the square root function, if you run that, This is known as basically a permanent function. And basically what that means is that calculating this is just embedded in another language, and it's very simple code. So you won't actually see it. A lot of the stuff in a lot of the base functions anyway, are actually coded in the background in C and compiled in C or some other language. And in that case, you may not be able to see the code here. But if you see something like square root, I think possibly sum might be another one. That, yeah, it's a permanent function, so you won't actually be able to see the code. But for anything else, any of the more sophisticated ones that are coded in R, you can type in that function directly without any brackets and see the code directly, which is helpful if you ever need to know what it's doing. If you just want to make sure it's calculating things in the right way, you can pull that up there. Any questions there, Erica?
Yeah, so somebody related to what you're just mentioning, somebody asked, question mark, variance on the console produced no result. Please explain. Does that make sense?
Yeah, it does, yeah. I'm not sure why I wouldn't give you any results, to be completely honest. You should be looking at the help tab, and if you search something, it should produce some results. Maybe just check that if you go single question mark, it brings something up. If you go single question mark variance, there's no function called variance, so that won't do anything. But if you go double question mark keyword search, it should bring something up in the search results. Only thing I can think of is if it's something with the installation of R. So maybe either just try rebooting RStudio or reinstall it if it wasn't done properly. But other than that, I'm not completely sure. I may note that here, and if it persists, I may follow up with you individually.
Okay. There was also a question earlier as to whether people need to install both R and RStudio.
The answer is that you don't. So if you wanted to just work in R directly, you could do that. So if you go on your computer, you have R installed, and you don't need RStudio or don't want to use it, you can use R. Some people prefer just to use the base R without having extra fancy programs, but the answer is that RStudio is just an interface. You don't need it to use R, but it is quite helpful. It has a lot of things in terms of nicely docked environment windows, package and help embedded nicely, different, changing your background colors and things like that. It has better integration for packages and integration with GitHub if you're developing code and things like that. So it has quite a few helpful things that way, but strictly speaking, you certainly don't need it if you just need to use R itself.
All right, thanks. There's been a lot of discussions about the question mark versus question mark.
Yeah, basically the double question mark you just use as a keyword search in R itself for different packages and functions. So double question mark is just some sort of keyword search if you're not sure exactly what you're looking for, and a single question mark is specifically for a function. So if you know exactly what function you're looking for example, you know that there's something called the var function for variance, but you just don't remember how it works, or you want an example, you can do single question mark and it will take you directly to that specific function. And if you don't know what you're looking for, you don't know it's called the var function, but you're sure there's something that calculates variance, then you can do double question mark variance and have a keyword search, and from there you can hopefully find what you want.
And somebody here mentioned that not having a connection to the internet might be an issue.
Yeah, that's a good point, actually. I didn't think of that, but yeah, you may maybe connected to the internet as well, so confirm that. I was just going to say that I typically personally don't use the double question mark, only because then you have to sort through all these different functions, and especially if you have a lot of packages loaded, that can be kind of cumbersome. So I find that just Googling R how to calculate variance may provide better results until you have a specific function in mind, and then from there you can go single question mark var and find all the actual specific detailed pages or page that you need for that function.
All right, thanks. I think covered them all. There are a few small questions that I may just compile and have Rob send out later, just like minor things about how to change colors and so on, just so that we don't take up too much time.
Yeah.
But I think we'll move move on at this point and trying to capture them all, sorry.
Yeah, sounds good. I definitely want to make sure that we get to some of the applications and some of the closing slides, so we'll keep pushing forward here. This is just a quick example to show here that you can use the C function to build vectors, and you can combine variables and functions. So here I have A has a value of 1, 2, 3, 4, 5, and I combine it with the rep function, which produces 5 ones, and I can basically run that, combine it with the C function, and make a vector like that. So you're not limited to just variables. Subsetting is something that's important to mention here. So subsetting basically just refers to the square bracket question. So how do you get, if you have something that's 1, 2, 3, 4, 5, how do you subset specific values out of there, or just certain values by indice? So for example, if I make a vector called A has odd values from 1 to 29, basically counting by 2s, which is what I did in the sequence function here. Has 15 values. If I want to get just the first value in the vector A, I go A square brackets 1, and it will give me a 1. Similarly, if I go A square brackets 2, it'll pull out that second value, which is a 3. And you can also do, obviously, subset multiple values at the same time. So if I go A square brackets, pull out the first and second values with this C1 and 2, I'll get the first 2 values, which are A and 3. Can pull out the first 3 values, 1, 3, 5, etc. This 1 to 3 is a helpful operator. So basically, if I say 1 colon 3, you can read the colon as 2. So 1 to 3. So if I go A of 1 to 3, I'll pull out the first 3 values. And you can also use a -1. This is maybe, again, kind of a quirky behavior, but A of -1 basically means give me the vector A, but without the first value. So minus or take away that first value. So you see everything from 3 to 29 without the value 1. So I will just keep it there for now, but basically to go back to that first question, square brackets are how you enter subsetting for vectors or matrices. Booleans are basically Boolean is just a 0, 1, a true or false kind of variable. So this 1 greater than 3, this is basically as a question, is 1 greater than 3, and you get the answer false. Similarly, is 1 less than 3, you get a value true, etc., etc. Is 1 equal to 1? Turns out it is. The useful part is that we can use that to actually subset vectors. So if you recall, A has these values. If I go, is A greater than 5? As R does, it applies that statement to every value of A. So you see the first 3 are, strictly speaking, not greater than 5, and the rest of them are. And if I wanted to pull which values are greater than 5, I basically can use that as a query in R to subset the values of A. And you can do some more complicated stuff here with multiple conditions. So I have something here to say A greater than or equal to 3 and A less than 20. So if I basically put that into my square brackets here as a subset, I'll pull out all the values from A which meet these criteria and these criteria. So it basically cuts out the 21 and 29 and also cuts out anything less than 3. There's also a function directly called subset, which basically does the same thing, but with different syntax. It basically just subset A, and then you can put in your statements directly as an argument. Similarly, there's this function called which. So it basically returns which values from A are greater than 3, greater than or equal to 3, sorry, and less than 20. And all these basically produce the exact same output. It's just different ways to subset. Okay. So if you're interested in more about that, you can use the single question mark to find out, but here's a few examples of subsetting vectors.
So Rob, there was a question related to that. I think someone was seeking clarification. So when you when you use parentheses to assign something to a variable, does that make it a vector?
So when you use parentheses to assign something to a variable, does that make it a vector? Specifically here, we're using the C function, which is the concatenate. So if we go help for the C, this is basically something to combine values. So when we call the C function, we have to use round brackets because that's the syntax for functions. And the way that the C function works is all the inputs to that function, such as 1, 2, 3, 5, whatever, those are all different inputs, input variables or values. So in this case, that's why I'm using round brackets, because I'm actually calling a specific function. Again, because people don't like to type things out too many times, it's just a single letter. It's still a function, if that makes sense.
Yeah, and then one last one before we move on, sorry. Somebody's asked, why did the last command generate a result with 2?
Yeah, I was just looking at that. I had a feeling that would come up. Here we go. So if we go A, what did I give it? So if we look at this, this is pulling greater than or equal to 3. And if we say which, sorry, so the which function on its own actually just returns the index values. This is these 3 here, these 3 lines, these are all getting values directly out of A, and this which function on its own actually returns the index values of that vector. So it's actually not returning values of the vector itself, it's returning the index values. So this 2, 3, 4, those are the positions in the vector A, if I pull it up again, which correspond to the statement. So it's actually referring to which ones are greater than or equal to 3 and less than 20. It's the second value, it's the third value, it's the fourth value, etc. And if you see how that corresponds to A, you'll see that matches up. So sorry for the confusion matching that together, but that's how the which function works. That should be separate there.
Great, thanks. We can move on.
Yeah, good question there. Keeping me on my toes here. So if we look at, I think this is actually pretty straightforward here. This is just getting into data frames. So you can make something called the data frame. As I mentioned, this is basically looks like a matrix. If we go data frame with A and B, that's the vector A, that's the vector B, and this will basically just mash it together. You'll notice here that it basically repeats the other one to get the same number of rows to match up. But you basically create a data frame with a very basic data.frame function, again with the round brackets because it's a function. If you go type of with that, you'll actually find that this is a list based on the way it's been stored. The number of dimensions are 15 and 2. So that's basically referring to the number of rows and number of columns. If you make another type of object here, matrix with the matrix function, you'll basically create with this command a matrix full of NA values, which is just not available, similar to non-number, not strictly speaking the same thing, but just basically blank values with inputs here for 4 rows and 4 columns. So if we call the value D, it's basically a 4x4 empty matrix. And if you go type of, you'll get logical, which is what it's filled with. Right now it's NA, so that's what it's referring to. And the dimensions are 4x4. So basically, in terms of the types of variables, you have these types of structures. So far, we have atoms, which are just single values. You have vectors, you have matrices, and you have data frames. And there's also something called lists. I won't get into that now, but you can basically use these different functions to check which types are which. Okay. This is just more with subsetting. Just a quick note that for matrices, the syntax is very similar with the square brackets, except when you have multiple dimensions, such as the 4x4 matrix, you need 2 references. So for example, matrix C looks like this. If we go 2x2, that's basically saying, give me the value from the second row and the second column, which you'll find is 4. So if we run this, we'll get a 4 back. If we leave that section empty, it'll basically return the second row and all of the columns. So it basically returns that second row there, marked by the number 2. And if we go the other way where we get square bracket comma 2, that'll basically be all the rows but the second column, which it outputs like this. So that's basically just a quick note on how to do subsetting for multi-dimensional matrices and data frames. Okay. And I alluded to this earlier, but just a quick note, you can actually use this assignment to replace values, specific values within vectors. So if we look at our D matrix here, currently it's empty. And if we want to fill all the rows second column, so looking at this here with basically repeating the number 2 4 times, we can run that command, replace specifically the second column. And if we look at what D looks like, we've now replaced those specific values. And there's a few other examples here, but they basically all do something like that. So there's a few examples of syntax for matrices. I'll do one more quick section here, and then we'll take a few more questions perhaps. You may have seen, if you've done some basic R stuff and looked at scripts and wondered why is there a $sign everywhere. Basically, the other way to refer to columns and sort of sub-objects, I'm not sure exactly what the right terminology is, but basically some subset of that object is with the $sign. So if you look at the matrix C here, you'll notice the columns are labeled A and B. If you go use the names function, you'll see that those are the names of the columns, A and B. So one way you could refer to that column A would be all the rows first column. That'll give you that as well. If you go see $sign A, because the column of A is actually, column of C is actually called A, you can use this syntax as well with the $sign to refer to it. And this is basically getting back to that object-oriented type of logic where A is basically stored as a subset of C. Similarly, you can use with quotes, it'll give you the same result. So you can refer to names of your variables if it's stored in that type of structure with the $sign. Okay, a couple questions, I'm sure.
Yes, so we have one question asking, is there a way to count the number of indices that meet meet a criteria?
Count the number of indices that meet a particular criteria. Is that the question?
Yes.
So essentially what we could do is if we go back to this which function. So this, if we remember, this is what A looks like. If we run which greater than or equal to 3 and less than 20, we get these indices. And if we wanted to check which indices match a particular criteria, we could basically just nest this. So we could say which of these, this basically this which statement nested in here is just a vector. Once you evaluate it, turns into a vector. And so we could say greater than 2. Sorry, here we go. But essentially, let's simplify this here. I'm getting myself confused. If we run this, store it into a variable. These are our indices. Oops. Oh. There we go. Too many back and forth variables here. Okay, so now we've stored our indices into here. We could just say which D greater than 2, for example. And so basically the answer is you would just nest your function there. So you would use which to get the indices. You could call which or any of these other criteria to check that logic as well. Similar to anything else. Once you evaluate this which function to get indices or any other way to get indices, it just becomes another vector that you can play with. So if you wanted to do that one line, you could basically have which round bracket, call your which, and apply another test for criteria depending on what indices you're looking for. Hopefully that makes sense.
Thanks. And then there was another question asking, can data frames hold non-numeric data?
Yes, they can. So if we say, let's just do a quick example here. So if we make A as, you can use the C operator in a few different ways here. So it doesn't have to be numeric values. It can be string values as well. So A has that. We'll go from 1 to 3 with this. So A looks like that, B looks like that. And if we go data frame A and B, now we have a mix of string values and vector values. You just have to make sure that A and B themselves, when you build a data frame, don't mix up alphanumeric stuff. So if you, oh, does that work? Yeah, so if you go and try to basically put numeric and vector, numeric and string into one variable, then that won't like it. It'll try to convert everything to a string, or depending on what you do, it might give you an error. But the data frame itself can actually store string and numeric values in separate columns. And if you try to do that with a matrix, so if you try to say, let's say matrix A and B, okay, so it doesn't give you an error, but it does just convert everything into string values. So I guess the difference there is that matrix, you can only store one type of value, whereas data frames, you can mix them up. Yeah, so good question.
Okay, I'll just say one more question, then we can move on. I am trying to capture them all, so we can maybe just send out a list of answers at a later time. But so the last one that we'll answer is C excluded and a variable name?
This is looking at the C command that we've been using to make vectors.
I believe so, yeah.
Yeah, no, C is strictly speaking a function. So, oh, I see what you mean, because we've now made it into data as well. Yeah, so in this case, if we go, I guess the proper terminology here would be that we've masked it. So because we've assigned something called C, that's stored as a variable in R. And if we call it basically to look for help as a function or run it as a function, then it will be operated as a function. So if we wanted to see what it would look like, if we want to see the code, we could use remove function, get rid of the variable, and then look at C, and now it's known as a function. So that's a good question. I guess you have to be careful in terms of variable names and function names, and it will basically override certain ones in R depending on how you've set up your script and stored your variables. So I suppose, yeah, while there is a function called C, you can assign something with the variable name C, and then if you try to call it, you'll get the variable name instead. Good question there.
All right, thanks. I think we'll just move on, but I am noting all questions.
Okay, perfect. Yeah, like I said, there's some more fun stuff, especially for people who've used some R before in terms of other functions and packages to get into. So yeah, we'll get into this section here about exploring and installing new packages. So installing new packages is super simple. You just do run the install.packages function with the round brackets and get the function, or sorry, the package name in quotes. So if I run this, I already have it installed, but it'll basically install the ggplot package directly. You can also do that if you don't want to type the command under tools, install packages. This is referring to that central repository with R packages called CRAN, and you can basically type in the function, or sorry, the package name, and it'll pull up, and you can install that package with all the dependencies directly. So now, in order to actually load the package into the R session, currently when it's installed, it's simply installed on your computer. It's not in your current R session, so you won't be able to use that package just yet. But if you use the library command, that pulls it up, and now I have this package called ggplot2 loaded into my session. And if I start trying to find what's in ggplot2, these are all functions stored within ggplot2. Before you call the library command, it won't know what that is. Here's a quick way, if you call this ls, which is just to list, package ggplot2, this will basically give you a list of all the functions that are in there. You can use that single question mark as well, and it will pull up the help page for ggplot2. So there's a few ways to start exploring packages there. There will probably be a question about this head function. This basically just gives you a preview of the first, in this case, 40 indices of what that output is. And this is just to truncate it because there's a lot of functions in here. So I don't want to overwhelm the screen, but yeah, just throwing this list of all the functions in ggplot2, the package, into this head function so that I only get the first 40 of them. Okay, so let's just keep exploring with ggplot2. So we have that library loaded. There's sample data called diamonds, which is just a big database of lots of different diamonds, diamond information, sorry. That head function I was talking about will give you a preview. The default is the first 5 rows. So this is the database, has different columns. And here's the first 5 rows, and that's just kind of a good way to see what that data set, table, data frame, whatever you have looks like. And here's a bunch of different functions you've seen before. Class, so it has, in this case, a few different classes. There's a table class, data frame, table data frame, so don't worry about that too much, but you can basically use that to see what, strictly speaking, class it is. Type of, technically speaking, it's a list here. If you go names diamond, this gives you all the column names, so you can see what data columns are within this database. STR will give you the structure of it. So this is basically a more detailed look at those different column names. So it gives you the name, sort of the data type, numeric, integer, that kind of stuff, and a preview of some of the data. The summary function will basically give you a quick summary in terms of quantiles and different statistics for each of the columns. So very helpful to see, mathematically or statistically what those different, what all the columns in that data set look like. And then end row and end col are just the number of rows and number of columns. So I guess that was probably pretty quick, but there's just a lot of functions there to help you understand what your data looks like very quickly. And if we go trying to subset here, back to this $sign, so we know that if we go names, diamonds, there's different column names here, which can be referred to. So if we go diamonds, $, caret, this will give you basically the caret column from that diamonds data set. I believe if we remember, there's something like, oops, if I spell it right, 53,000 rows, so I don't really want to call that, but if I did, it truncates it, so it gives me the first 1,000 and then cuts it off for my own sanity here. But if we go head, diamonds, caret, it will basically give me the first 5 values of that data column. Pulling in some of the power in R here, if we go mean, so the mean function or average, and go diamonds, $ price, this will basically give me the price column from there, from that data set, pull it into the mean function, and I immediately can calculate the mean for those 53,000 rows. And then this is basically putting a few things together. But if I want to create a new variable called my database or my DB, use the arrow operator, here's diamonds, and I use square brackets with the subset to basically say, give me the diamonds database, subsetted to where diamonds, the price of the diamonds from this database is greater than 3,000. So I can do that, and now I have a new variable called myDB, and it has some subset of that diamonds database, which will fit this criteria. So if I go summary, myDB, look at the statistics, you'll find that this price minimum starts at $3,001, which makes sense since I just queried everything with the price of more than $3,000. Quick pause for questions there, Erica.
So there's a question that was asked. I guess it was actually in before we were taking the other questions. How do you refer to a row in a data frame with a percent sign?
With a percent sign? I'm not totally sure. Is that the $sign or? I'm not totally sure I understand that.
All right, maybe we'll skip this one.
Yeah, there's something called pipe operators which use percent symbols. I won't get into that now. That's something different. Okay. Yeah, I'm not sure if that's what that question is getting at, but maybe we'll save that for the follow-up.
It was a $sign favorite.
It was, okay, yeah. So basically, there's column names and there's row names as well. Row names are not typically used, but theoretically, you can assign row names to your data frame as well. And then the syntax will be, I think, pretty similar. Again, to be honest, I'm not 100% sure if that's true, just because row names aren't used very commonly, just the way data is stored. But you could theoretically refer to, in a data frame, instead of the row reference by number, you could use the row name as well, similar to the way the columns are called.
Okay, and then here's the last question. It's in general, how do I uninstall a package?
Good question. So I guess RStudio is kind of sneaky in that it has an install.packages very readily here, but doesn't have an uninstall. So if you go to the packages tab here, you can basically click on one of these, or sorry, not click on them. If you click on it, I'll give you some info about it. But if you go to packages, you could just click the X here, and that will uninstall it. But I guess that's the proper way to do it. Technically, all these packages are just stored somewhere on your computer, likely in the C drive under programs, R, library, something like that. So you could just delete those folders as well if you wanted to. But yeah, the proper way would be to go through here and just click this X, and that will remove the package from your computer. Okay, let's move on here. So I mentioned that there are sample data sets that you can get from packages. There's also a number of sample data sets stored directly in R. So base R has a function called data. So if we run that, this basically gives you a window into a whole bunch of sample data sets. So there's quite a few here. Again, these are sample data sets, probably not useful for any of your own actual analysis, but what they are quite useful for is making reproducible examples. So if you're testing a function or you're writing a script and you want to basically send it to someone else, you don't necessarily have to send all your data. You can just use one of these sample data sets. So from the, actually, let's run this one more time. Somewhere on here, there should be something called CO2, if I can find it. Anyway, somewhere in here, there's a data set called CO2, just like this. So if we go head CO2, that'll give you a preview of the first 5 values. Here's a little sneak peek into plotting. There's a sample data set right there. So this, I just threw this into the plot function. There's all the values for CO2 concentrations and parts per million in the atmosphere with time. And there it is. So lots of helpful sample data sets there. Something that's maybe, I guess, equally applicable to water resources people, maybe more so. There's a Lake Huron data set. So if we say summary, here's the Lake Huron data set. And if you want to find out more about it, you could go Lake Huron, and there's help for all the data sets as well. So here you see the description, annual measurements, and the level of Lake Huron in feet from 1875 to 1972. So if that's a useful sample data set for you, it's built directly into R there. Okay, so let's get into the meat of the CSHS hydrology package. So this package, let's plug the paper here for a second with the browse URL function, which you can basically just put in a string web link, hit browse URL. I won't do it now because I don't want to interrupt our studio session here, but that will basically open up in your default browser to that link. And if you haven't checked that paper out, feel free to do so. That just gives you a bit of a discussion in the Water Resources Journal on what the our package, the CSHS hydrology package, is all about. The package itself is now on CRAN as well as on GitHub. The latest version, if you want the latest, is on GitHub. There's a package called DevTools. So if you install that, bring it into your session with library and use the command install GitHub, it will basically install this package. And any other package, if you want to do a different one on GitHub, you can just put the address in here and it will install it directly in your R session. So that's part of that integration with GitHub that in this case, R itself has with the DevTools package, and RStudio as well also has. Anyway, so there's the few lines of code if you want to install the CSHS hydrology package directly from GitHub. So if I load it into my session here, one way to view all the functions in the package as well is just, to get help on it, is just to go the package name, and it will bring it up. And if you want to view all the functions in the package, you can use that ls function that was mentioned, and that will give you all the functions that are in that package. So that's another helpful way to, if you're interested in the package, think that it'll be helpful but don't know exactly which functions to use, you can use that. Any questions there about installing things from GitHub or installing packages in general?
We do have a question. If there are conflicting function names within packages, and if so, is there a hierarchy that's assigned to them?
Good question. So in terms of hierarchy, I believe the package that's loaded first will basically take precedence. So if you load something that has a function name called date, I guess in this case, date is actually a function directly in R. The date function just returns the current date, and if you load another package later that has a function also called date, and you just try to call date on its own. For example, there's a package called LubriDate. We'll get into it later, but it has another function called date, and you'll see there's a message here that the following object is masked from base package, function called date. So if you now try to call date, you'll still get the original. And if you want to call specifically this new package's date function, you basically go package name, double colon, and date. So yeah, in terms of hierarchy, the one that's loaded first will take precedent. And if you want to refer to a specific function within a certain package, then you just basically call it with the package name, just to avoid any confusion. That's been at least in my work with time series stuff. Every time I loaded that library and tried to call a date function on error, it was always confused me. So that's a good tidbit there in terms of making sure you're specific about which function you're referring to when you have multiple packages loaded with potentially conflicting names. So great question there.
Okay, I think we have some that are a little bit more general, so maybe we'll just move on so we can cover this topic.
Sure. Yeah, depending on how we go do for time here, we can take some general questions at the end after the presentation, or maybe leave it for a follow-up as well. Just in terms of some plotting functions, so we looked at plotting the CO2 data. There's some different arguments here for spicing this plot up. This is probably not something you'd want to put in a report directly, but for example, the COL for color function, or sorry, not function, the COL parameter within the plot function will let you change the color of the plot. LTY for line thickness, I believe, or sorry, line type rather, will give you the line type. So if we change color to green, line type to 5, we get a different type of line, different color. Similarly, we can make this red with the color argument. LWD is line weight, I believe, and that will basically change the thickness of that line. So there's lots of easy ways to play with the plot function. There's also, and again, if you go $plot, you'll get a whole description of all these different parameters and their usages and examples. So I won't go into too much here, but just as one example, there's a parameter for xlab, or label on the x-axis, ylab, and main, which is the title. And so there we go. That's now starting to look like a more publishable type of plot. So that's just an example of how to spice up your plots and make them look more proper than just the plot without any parameters, something like that. Okay, and if we look at getting back to the CSHS hydrology package, if we load that library, there's a data set, sample data set in the package, which is this W05AA008. When you go, but let me just clear this for a second because there's a lot here going on. So if we load this back, there's now this data set. If we apply the head function to that sample data set, we get a sense of what it looks like. If we apply the summary function, you get all the statistics for those different columns. And if you go ? Name of the data set, you get the help page from the CSHS hydrology package. And you see that this is basically a data frame from the Water Survey of Canada, which you probably could have guessed based on this layout. And it's from the Crow's Nest River in Frank, Alberta. Okay, so there's just how to load some of the sample data from that package. Just another example of querying from there. So we have our W05 data, and if we want to get just the flow data, if you're familiar with the WSC parameters, one is the flow data. So we can run that, and now we have just flow data, and now we can throw that into the plot function, and there's our flow data. And again, this looks quite messy, but there's just what the base plot looks like, and we've used the sample data from this hydrology package to do so. Yeah, I might skip over this just in the interest of time, but you can play with this just with different plot arguments to get something that starts to look like a respectable plot here. This expression just basically is a syntax to get, it looks a little bit messy, but not too bad once you go through the individual pieces, but it's basically to get that superscript there with the expression function, and AV line is a nice little function to just basically draw a line on top of your plot. So if we have an existing plot, we draw an AV line where the horizontal is equal to 25. We can set the color, line weight, line type, that kind of stuff with the same parameters. And now we have this orange line exactly where we want it. And one other quick note before we get to questions is if you want to save this plot, if this is a nice plot that you want to put into your report, save as an image, you can go export, save as image, or save as PDF, save it under a file name, hit save. Or if you're doing this in an automated way and you don't want to make 100 plots and hit save 100 times on your interface here, you can use the PNG function to basically create a PNG of that plot directly. The way it works is you basically run this PNG function with an argument for the file name. So this will basically create an empty file here called My Fabulous Plot. This redirects now everything that follows in terms of plot commands into that file. So I would run this plot, I would draw my line, and then I would say dev.off, which basically just stops writing to that PNG file. This basically just tells me that I've now stopped writing to it, and now I have an image file with a .png extension in my Active Directory called My Fabulous Plot, and there it is. Again, you probably want to play with this a bit more to make it look pretty, but that's how you would save your file to the file. And just to wrap up here, this getwd, this is get working directory, so that will basically tell you where this your Active Directory and where that function was written to if you didn't specify it in the file name. And if you say list.files, that basically tells you all the files that are in that Active Directory, which are, of course, the same ones that I have under my files tab here. So that's basically it for the plotting. Any questions on making plots?
Yeah, someone has asked if they can easily put a secondary vertical and horizontal axis on the plot. For example, for a rain event, on the top axis plotted as an upside down column graph with intensity on the second.
Yeah, good question. So yes, you can do that. I don't have it in this webinar just because the syntax does get a little bit messy. If you Google add second axis to our base plot, you'll get a result there in some examples. But essentially, you would make a plot with two axes, and then you would write the data to one axis, add the data to a second axis, and you can basically, as one of your arguments, target which axis you want to plot to. I don't have an example of this here, but you can also, if it's easier to show, you can basically make a like one single plot image with multiple plots in it. So you basically can tile off in 2x2 or 1x3, whatever layout you want, and target different plots at different sections of the image, if that makes sense. So you could basically have, if you go 1x3, for example, have one plot underneath another plot underneath the third plot. So yeah, there's lots of options that you can do there in terms of plotting different axes, having multiple plots on the same page, adding different lines and points to the same plot. Yeah, I don't have an example of a second axis here, but there's if you just Google that, there's definitely an easy way to do it.
We've actually had a couple questions related to being able to set the resolution of the PNG. Is this possible?
Yeah. Yeah, sure. I'll just say generally, again, just in the interest of time, just want to keep things moving here. But if you go $PNG, you'll see there's lots of different functions here. You can probably guess which formats these all output to, but there's different arguments here for the width, height, the units for the size of the plot, and there should be a resolution in there as well. So yeah, you may have seen that plot that was outputted here, this fabulous plot. It's maybe not exactly fabulous yet, but if you wanted to play with the different arguments in the PNG function itself, you could set the height, width, resolution, all that kind of stuff. And then if you adjust that, then you could do a plot that looks a little bit more publication worthy.
Okay, maybe we'll just do one last one. I'm not quite sure what this question means, but can we do subplots with R?
Yeah, sorry, so subplots, that's the term that escaped me, but that's basically what I was talking about with the different tiled plots. So for example, if you do, to be honest, I don't remember the syntax, but if you use a subplot, it might even be a subplot function actually, but that's basically what would allow you to write multiple plots per image to have, let's say, a 1x3 set of plots or 2x6 or whatever you want to do. So yeah, I'm guessing that's probably someone familiar with MATLAB, and there is a similar or same function to make those types of subplots in R.
Yeah, that's great. Thanks.
Okay. Some of this, so I have a section here on basic programming stuff, as I've called it. This is basically the if statements, the for loops, the different logics, that kind of stuff. I won't spend too much time here because I think this stuff is relatively straightforward, but here's just a few examples of what this kind of stuff looks like. So for example, if I have a with a value of 5, here's the structure for my if-else statement. And this basically says if a is less than 2, run this clause, otherwise or else do this. So since a has a value of 5, it's definitely not less than 2. So it goes to the second statement here instead of the first one, and only does the one that's appropriate based on the logics here. I'll skip this section, but this is basically just another way to set up and test that logic. So that's the syntax with if statements. There's a few variations on that, but essentially if-else statements will look something like that. And just to preempt the question here, you could say else, add another statement, a is less than 3, try something else, and then have another else statement in here. So you could basically have if else if, and have multiple blocks here if you wanted to. Loops. So this is really where the power of programming, especially, well, not especially, but also in R comes in, is to basically be able to automate and do things in an automated way automatically without having to sit there and run it yourself. So for example, here's a very simple for loop. We're declaring, in this case, a variable called I. So for I in the values of 1 to 3, we're just going to print that value out. So if we run that loop, I've now printed this value out 3 times, and that's a lot nicer than going something like that. There's also a while loop and a repeat loop. These are basically just different formats. So the logic of a for loop is basically to do what's in this loop for these values. So from 1 to 3, it's going to do this, whereas the while loop will basically keep repeating this until I is less, while I is less than 4. So as soon as this statement is no longer true, it will break the loop, and the repeat will basically just keep repeating indefinitely until you break out of the loop with something like an if break statement. So that's basically just the different types of loops. Again, I don't want to spend too much time here because I'm looking at the clock. I do want to get to some of the applications, but hopefully there's enough there for you to play with some of the loops. And just one quick note here before we get to some questions. Loops in R are generally speaking relatively slow. Not so slow that if you're doing a simple 1 to 3, you'll notice a difference. But if you're creating a vector and doing stuff with it from, let's say, 1 to 1,000,000, you'll start to notice speed differences in for loops. And basically the quick note there is that some of the native functions in R, like the sum function or the square root function, are compiled in C, and they'll run a lot faster than if you sit there and make a for loop with R itself. So for example, I've declared this variable called dd, which is a sequence from 1 to 1,000,000. I've initialized my ss as the sum to calculate. And if I make a little experiment here, in one case, I've gone use the for loop in R to make this sum, to basically say from 1 to 1,000,000, which is the length of this vector, I want to take my sum and add the next value. And as a comparison, I've used the sum function to do basically the same thing, to take a sum of this entire vector. And you'll notice that here, the speed on the first one is 0.03 seconds, and the speed on this other one is essentially 0. And again, maybe for this application, you don't care if it takes 0.03 seconds, but if I start to go a little crazy, make this 10 million, run the same experiment, the time differences start to get a little bit more drastic. So here it took 0.4 seconds instead of 0.02. So basically just to say that loops in R are generally slow. Again, not so slow that you will, for most applications, notice a difference. But if you're doing some really big data crunching, it's better to use some of the built-in functions or a syntax that avoids for loops or any other type of loop. That's maybe a good pausing point for any other questions there, Erica.
We have one question related to loops, and then the other ones I'll maybe leave to the end. Is there a need to update the index variable for loops?
Good question. So for for loops, there is not. It will take care of that automatically. The reason I have, if we go back to this example for I in 1 to 3, you'll see it prints the value of 1 to 3, and there's nothing else in here. So it'll basically automatically, just the way that it's structured, go from 1 to 3 based on the values that input in here. The other ones, such as the while, will not. So if I were to take out the thing that increments, like for example, if I start off with I as a value of 1, run this, it will run from 1 to 3. And then as soon as it increments to 4, this breaks. If I didn't have this statement here, the value of I wouldn't change, and it would basically keep going infinitely. So that's a bit of the difference between while and repeat structure loops and for loops. So to answer the question, no, for a for loop, it does that incrementation automatically based on what you've inputted here. The other types of loops will not do that automatically, which is why I have incrementations in here built in.
Okay, I think we'll just move on.
Okay. This is maybe a little bit less time than I would hope for some of the more exciting stuff, but here's some of the actual applications. So this is probably the type of stuff that everybody on the webinar is more interested in. So here's a few examples actually in hydrology and water resources. So for example here of different packages is scraping Environment Canada data, specifically meteorological data. If you've gone on this website here, you've probably found that you have to, for anything less than, I believe monthly, you have to basically download 1 month at a time. So if you want to get hourly.
Have you switched screens? Because we still see your console.
I'm still in our studio here. Hopefully you can see it.
Sorry, I thought you jumped to the presentation. My bad.
Oh, no, sorry. Yeah, I'm just looking at this link here. I'm still in our studio, but if you open that link or if you're in the PDF and you click on that hyperlink, it'll take you to the meteorological data website from Environment Canada, where you can download data in a lovely way, 1 at a time, 1 month at a time, which if you want to do 30 years of analysis on data, that can be a little bit cumbersome to download all those different months. So here's one example of a package called WeatherCan, which basically stitches that data together for you. So if we run this, install the package here, which is on CRAN, and basically with this simple command, WeatherCan, we're just referring to this package and this function name within the package, station search, with the name Weller. We basically find all the stations that are in the database from Environment Canada with matching the name Weller. So you'll see that there's, the way it's stored here, there's basically a station per each interval download. So there's Port Weller with daily, hourly, and monthly data download. And as an alternative to downloading from the website, if I just want to use R with this WeatherCan package, run the function weatherdl or weather download. I'm going to say I want the station ID of this station. There could be multiple here if you wanted to. In this case, I'll just take this Port Weller data with the station ID of 7790 and set the interval for monthly data. I run that, and in 0.3 seconds or however long that was, I now have all the monthly weather data for Port Weller downloaded. Port Weller, I mean. So if I say head my variable here, you see that now I have these columns as well as all the other ones listed here. And if I want to make a quick plot of the average monthly temperatures at Port Weller, I just say plot Port Weller $mean temp, and here's a plot. So very quickly, in about 3 or 4 lines of code, I can load the library, find which station I need, download the data, and start making plots with it. And there's a few other, WeatherCan's not the only one, but it's the one I tend to use. There's rClimate CA as well, it does something very similar. There's, I'm sure, a few other packages, but there's at least one very quick way to download the meteorological data from Environment Canada. Something that I'm sure people are interested in is reading and writing with CSV and Excel files. I won't spend too much time here, but basically there's a function called write.table and write.csv, which writes to data format specified by the separator you provide, the file name you provide, and the data you provide, and a few other arguments as well, but basically 1 line of code. And I can now have a file in here called portweller data.txt, or if I prefer CSV format, write.csv. I have a port weather data .csv file. So pretty easy to write data to files. There's also a read.table and read.csv set of functions which just do the opposite. And one more note here before we take a couple questions. There's an XLSX package. When I was running this yesterday, I realized that you need Java installed on your computer. So if you don't, if you're unable to install this package directly, there may be some issues with Java on the computer. But essentially, this is a library to read and write from Excel files. The syntax is very similar, write.xlsx and read.xlsx. And essentially, it works the same way as these other ones. It just writes to Excel files. Only difference is you have to specify the sheet name because now there's multiple sheets in an Excel file. And that's basically it. So if I run this, I take my port weather data, and I now have an Excel file with port weather data embedded directly. Of course, there's a few more parameters and things you could play with, but in 1 or 2 lines, that's how you read and write from data files. Erica, any questions there on that?
No, we don't have any questions specific to this.
Okay, I'm sure there will be once people start getting into it, but here's a few examples, and I'm sure that you can find some more in terms of parameters with the question mark function name. Here's one that's very useful for anyone working in water resources, is scraping Water Survey of Canada flow and level data. And again, there's probably a few packages to do this, but a good one is tidyhyddat. And this is also available directly on CRAN. So if you install that, you load the library. The first time you do it, you have to download the hyddat database, which if you've used the Environment Canada Data Explorer, ECCC Data Explorer, I think it's called, it basically has the Access database version of hyddat stored in it. So you have to download this to your computer. But then once you have it, you can basically, similar to the other Environment Canada scraping tool, you can scrape flow and level data by station number directly. So here's a quick example. I have this library loaded. I'm looking at the Grand River at Galt in my own watershed here with the station number 02GA003. Sorry, that's a 02GA003. And I just specify the station number, use the function hy daily flows, and one line, I pull all of the daily flow data for Galt. Similarly, if I want to look at Grand River at Brantford, I run that, and if I look at the data, I now have basically the date time series, parameter values, all the flow values, and the symbol that comes with the data for data flags. So again, much simpler than going to the website for Water Survey of Canada and downloading all the data separately and merging it together in Excel. There's a few parameters in here if you want to specify the date and time interval that you want to download data for, or if you want to download sub-daily or monthly, there's different functions in this package to do so. But here's an example for just getting all the daily flows from a particular station. Going into time series, I know I'm moving a little bit quickly here, but there was a request, I think a few requests were looking at time series manipulation. So there's a few examples here for handling time series, and I might skip over this for now, again, just in the interest of time. But essentially, if you read in the data, the important thing to know is that when you read data files just from CSV or something like that, it's generally read in as a character. As you can see by this class example, if you just go class of this data date, it's a character, and so you need to go through something like the as.date function to convert into something that's an actual date format. Specify the syntax as year, month, day, and once you have that here, it's now a date class as opposed to a character, and then R will treat it differently based on whether it's a string, in which case it won't let you plot anything, but if it's a date, it will know how to treat that. So if I make a plot, again, with this port weather CSV data, I've read it in, converted the string dates to an actual date object, and now I plot it, it automatically handles the years here for me. I think the rest of this I'll skip over for now. There were a couple talks internally about having future webinars, so there might be one on time series, so maybe I'll have more time to get into this kind of stuff then. But I'll leave that for now, and if you want to work through the PDF and follow up or email questions, then you can certainly do so. So I'll skip that. Just getting back to the CSHS hydrology package, there's a nice hydrograph plot function, which you can use to make nice hydrographs. So if I actually just go back and run some of this stuff, oops, there we go. So I'm just converting stuff into the right format here, so I can use my hydrograph plot from the hydrology package. So you can make in one line of code here, once you've got your data downloaded and converted, some nice hydrograph plots. And there's a few arguments built in here into this hydrograph plot function from the hydrology package to do things like winter shading and change labels and things like that. And yeah, there's an argument here for the period. So if you want to use the full period of data, it will do that by default. And there, with one argument, you can specify the date range to get just a specific water year in this example. Okay, I'll leave it there for now. Any last questions about this this R stuff here, and before we switch back to the presentation to wrap up?
I think we'll just switch back because we have 5 minutes, and there is actually another meeting that starts on this line after that. So.
All right, we'll wrap up quickly here then. Hopefully this goes smoothly here. Can you see the presentation here?
Yes, we can.
Okay, so just to wrap up the webinar, there's a few notes here, and I'll go through these a little bit quickly. Hopefully you've seen that installing packages from CRAN and loading them in and using the functions is pretty easy to do. One line command to install your package, install that packages, and it's accessible. And as you've seen, there's a lot of help documentation associated with all the functions, especially if it came from CRAN. So there's a lot of resources for loading and using new packages. There's other R packages on GitHub. So there's an example from my own repository. But if you don't find what you need on CRAN, you can certainly search GitHub and other resources, and you're not limited to R packages only hosted on CRAN. Building your own packages is actually surprisingly straightforward and easy to do. And I might leave it there except to say that Kevin Shook has a very good resource on that same link on his own GitHub page for the Center for Hydrology on actually building packages and different tools to do so and the process for that. And a note in bold here to say that the post-conference session, which is I guess what it was called, but it's now on the Wednesday for the conference itself at the national conference in a couple of weeks in Collingwood. The session on Wednesday will be actually about how to build your own packages and contributing to the hydrology package and that kind of stuff. So if you're interested in some information about how to build our packages, that'll be covered in that Wednesday session there. Here's just a few links for help resources. Again, just to emphasize, there's a lot of people working on this type of stuff. Some of the links here are good training resources or different R routines and handy scripts, and a good list of different packages that are useful in water resources applications that I didn't have time to talk about here. And lots of other resources, talking to colleagues, Stack Overflow, if you've never gone on there, and just Googling, here's this error in R that I get, what's the problem, is usually pretty fruitful. And of course, we talked about the CSHS hydrology package. Just quickly mention that this is a package built in a collaborative effort by Canadian hydrologists and water resources practitioners to build an R package which addresses issues in Canadian climates. No experience necessary to join or help out, and we'll be talking more about it at the national conference. As I mentioned, there's the sessions on Wednesday. First two will be basically a two-part workshop discussing building packages and the R hydrology package itself. And there's an afternoon session about new functions being developed in R within that group. And just a quick note that there are spaces available for some of the other conference workshops, such as the flow forecasting with WattFlood one. So if you haven't registered for a workshop and you'd like to, please take a look at the conference website and book yours soon. And just to end off here, thanks for everyone for signing into the webinar here. As Erica mentioned, there will be some follow-up. These materials will be made available. Likely send out a follow-up survey just to see if there's anything that can be improved for future webinars that we hope to do. And there's my contact information if you'd like to get in touch directly with our questions or our projects. So with that, I'll turn it back to Erica. Thank you.
All right, well, we only have 1 minute left, so I just want to take time to say thank you, Rob. That was very informative and I think very well laid out, and I'm sure that the recording will benefit many people beyond the 100 people that already joined. So thanks again, and we hope to see people at the conference. Also noted that the CSHS annual general meeting is held on Wednesday at noon, and so come by if you'd like to get involved. So thank you, Rob.
Yeah, thanks, Erica, and just thank you to CWA and CSHS for setting this up and hosting. Thank you.
Excellent. Take care, everyone. Bye.